Tēnā koutou katoa, ko Di Misinaho. I am a senior researcher from the Bioeconomy Science Institute, formerly known as SCIEN, formerly known as the New Zealand Forest Research Institute. So as long as everyone's got that head around that one. Today's presentation is on from sensors to analytics, development and operation of the forest flows big data analytics pipeline for complex environmental data. So it was interesting with the previous session talking about solutions kind of from a strategic top-down approach, and this work was kind of more of a bottom-up approach in bringing analytics and big data to answer a problem. The problem was around trees, water use and forest water yield. So over the last decade there's been increasing concerns from various groups throughout Aotearoa New Zealand around freshwater availability and quality, impact of large-scale forest plantings, how much water radiata, pine and other tree species use, downstream impacts on water supply, and on top of that there's been little research in forest hydrology in the last 40 odd years, so there's been lack of data and information, and this information black hole has been filled in by commentary by the examples on the right. It's amazing what you can put in the media there with just your own opinion or asking someone else with opinion without any fact checking. So Forest Flows was born to kind of fill in this data black hole, and this was the Endeavour program that ran from 2019 to 2024, finished up last year. Loads of fun trying to run a 5-year MBIE program during the COVID pandemic. And this involved setting up a total of 9 research sites across the country, including 5 primary research sites, which are the sites in orange across the rainfall gradient, from 800 millimetres per year to about 3,000 millimetres per year, and with different climate, geology and soils. This is an example of a primary research site at Mahurangi. Each of those points on that 36-37 hectare catchment represents a research plot. Each research plot had a flow lab datalogger. We hoped to buy a datalogger off the shelf to run on multiple types of sensors, but they came very expensive, so we had to develop this datalogger from scratch with a Croatian company called Impact, and that runs on a wireless IoT network. Each of those flow lab dataloggers had 4 steam dendrometers. That's an example of the pictures on here on the right, and that measures low-cost sensor to measure daily tree growth and water use. Also in each of those flow lab dataloggers was 4 soil moisture sensors, and they measure soil moisture at 4 different depths. So it measures how much water is in the soil and how much water is moving through the soil during rainfall event. And each of those sensors will be taking measurements every 5-minute intervals. So Forest Flows relied on a combination of this new GWIS technology of sensors, as well as traditional forest hydrology techniques, was integrated together with the various remote sensing measurements from satellite, and as well as periodic measurements from airborne sensor platforms, as well as terrestrial data taking measurements above ground and below ground, sensors taking measurements every 5 minutes, as I mentioned previously, as well as various static measurements. So in total we had over 1,717 instruments taking measurements, which equates to about 360,000 data observations a day, which equals 130 observations over a 12-month period. So we succeeded in having lots of measurements to understand tree water use, catchment water storage and water release. We're like, hooray! And then we're like, oh, how do we manage all this data and analyse it? And that's where we went to talk to my friend Albert and the TAIAO team at the University of Waikato. However, before the science begins, is that it's very important to say that engagement from local communities, stakeholders and iwi should be done from the get-go. One of the strengths of Forest Flows is that we started this conversation early and conversation often. We had the comment when we were working up in Northland. The comment was, oh, it's great you're having a talk with us today. What time is your flight leaving today? And we said, no, we're up here for the week, and the jaws just dropped. Having that early engagement and having that active engagement was very, very important. And that's because it built trust. Explaining why you're doing the research, how the research benefits the local communities, benefits them, not just, hey, we're going to write lots of papers and tick the MB boxes, and also how the community is involved. They want to be involved, want to be engaged. They don't want to be just passive passengers on this journey. Doesn't excite them, doesn't bring them on board. And there's a lot of passion I found working in local communities, rural communities around New Zealand. They want to understand what's going on in the environment. Talking to Māori can seem to be scary, but it isn't scary, especially around the joys around, especially with the conversations around data sovereignty. It's just, again, it's engagement early, engagement often, lots of cups of tea, and it's amazing how they can break down barriers, build bridges, and help build that partnership. Sometimes you're just going to get a flat no, and then you say that's all quantify, and you find somewhere else to work. But 9 times out of 10, that having those conversations early does amazing things. And also active engagement throughout the project, not just at the end. Nothing worse, one of the most upsetting things for the local community, if you come in the beginning and say, hey, I'm going to work with you, and then give us all your data, and then you disappear for several years and come back and show it at the end. That's going to get a lot of hackles up. So keeping them informed, sharing the information, making yourself available, as well as showing what it all means at the end is an important thing. So it's bringing in the local communities along with the journey, especially with Māori. So this work is around forest hydrology, rather specialised piece of work, but you can also think of this project as an example of working with complex environmental data. How do you collect data from multiple sensors and sites, that we just talked about? How to manage this big data from multiple sensors and sites? How to analyse this data in an effective, timely, transparent and biologically meaningful way? So that's some of the challenges we face. So we've already dealt with how to collect the data, which was hard work in itself. So how do we get all this data from our 1,700 instruments and 360,000 observations every 24 hours without being crushed? We did that by developing the Forest Flows Kafka Big Data Pipeline, where each of our primary research sites, the data being transmitted for our wireless IoT network was sent to a central gateway that was pumped into through the cellular network into the cloud, and it was clean, streamed and stored in Apache Kafka. If anyone's dealt with messy biological data, having an ability to clean that data as well as really tight nomenclature of the data coming through solved a huge amount of issues, just having that data stored and being accessible. No lost files whatsoever. It was amazing. Then we're working with one of our key collaborators, NIWA, now the Earth Science Institute, who brought us information about meteorological data, stream flow data, groundwater data, and they had their own set of data pipeline system, and with a lot of convincing, they would lead us to pipe it into Cache Kafka, have that data located at one place for our multiple collaborators to access the data, which was really important to have in the cloud, which we hosted in AWS, but we weren't locked into AWS products. We can up and pick the Apache Kafka and plonk it somewhere else. So we didn't have to deal with the joys of pesky firewalls, so various collaborators can access it both in New Zealand and internationally. We had our collaborators at the University of Waikato TAIAO program who were able to access the data directly from Apache Kafka, but pesky scientists like myself don't want to mess with the Apache Kafka, so we use a third-party interface called InfluxDB to download the data, and it was just amazing. Huge amount of data we had to pull down in minutes, what it would have taken days or weeks to compile with traditional methods. So, got the data, got lots of measurements, got the data around the forest, got the data stored in the forest, managed it very well, but how do we analyse it? So, Forest Flows provided, with our data measurements every 5 minutes, provided near real-time data on the pulse of the forest. It was focused primarily on forest hydrology, tree water use, catch water storage and release over time, but also gave us information about productivity and health. Happy trees equals fast-growing trees, unhappy trees like disease or drought, or means that you can see them slowing down in growth. We use a suite of analysis tools, statistical, empirical, process-based model, and AI. So I was using different statistical methods, analytic methods to answer the key questions. Some of them were multiple methods to answer the same question, some dovetailed in there, but it wasn't one method to rule them all. Statistical approaches were suitable for answer some, but not all the objectives. Brute force machine learning methods like random forest were not suitable considering the compute time and also trying to get the results sooner than later. So Forest Flows used a range of AI approaches we kind of collectively called Green AI. First was predicting temporal spatial variability of tree growth, water use within and between sites with deep learning neural network. Also forecasting with explainable AI. Spatial temporal prediction with data fusion of terrestrial and remote sensing data was in physics-based equations with neural ordinary differential equations, node. This presentation was talking about science making a difference in the real world, and also finally about dashboards and forecasting with streaming data. So the first one, predicting tree stem growth with deep learning neural networks. So this is the diagram on the right. Is a schematic of how the data was transmitted through the Kafka big data pipeline from the sensors in the field at the top there, moving into the Kafka pipeline. And we're very interested in using dendrometer, treated stem growth forecasting for one of the 5 sites at Ashley. So we used 25 plots, 100 dendrometers, 5-minute intervals over a 10-month period, and 7.8 million observations during that period. And we evaluated 4 deep learning models: CNN, LSTM, Transformer, and ETS Former. And we played around the forecasting range between 5 minutes and 720 minutes. And the best performing, to our surprise, was LSTM. They gave us high accuracy, robust temporal resolution, and they captured most importantly, captured the diurnal and the seasonal variation without large compute. And that came out in a paper earlier this year in ecological informatics. What was interesting about the results there is that the model told us the optimal collection time for data was every 3 hours. So we can reduce the amount of measurement time from every 5 minutes to every 3 hours, which has a huge benefit in saving resources in terms of data collection in the field and the amount being transmitted in the wireless IoT network. That was a biggie find for us. Secondly, explainable AI. So applied explainable AI to explain the predictions from our black box AI model that was kind of mentioned a lot before. We increased model transparency, interpretability, and trust. We used the explainable AI occlusion method, which used part of a trained model to modify a block, or otherwise known as include, variables one at a time, and then you kind of compare the forecasted model with the included variable for the original AI model. And this determined which environmental variables were important for forecasting an AI model. And this modelling approach worked very well for linear and non-linear responses to individual environmental data. So we took our friend dendrometer, which is up there on the right there on the tree, and we trained the model from the data from one site, from Ashley Forest site, and then we applied the model to Maharangi Forest, which has a lot more rainfall and different climate as well as different geology in soils. So represented here on the table here. So we're going from an environment that has about 800 millimetres per year rainfall, and then Maharangi has 1600 millimetres per rainfall per year. And this is looking at the results, some of the results from this occlusion method. So this is occlusion seasonal predictions using Ashley Forest trained model. On the model on the left-hand side, so it's been applied for Ashley data, and on the right is for the Maharangi data. This model did predictions on the weekly basis, and it gave us really good fit, but that became a bit mind-blogging for us mere humans, so we just looked at this on a seasonal basis of all these 22 feature variables of climate. And each of these blocks represents a response of the dendrometer, either a positive, which was red, or was negative, or was blue. The more blue, the more red, the more stronger the effect of that variable at that particular time. And what made us very valuable was like using traditional statistical methods, saying this variable is more important and then less important for the entire period. This is identifying periods of time where the environmental variable is more important than other periods. So if we look at these top 5 environmental variables between the Ashley site and the Maharangi site, both of those variables have more or less equal importance at the two different sites, but importantly you can see the colour changes over time, where those variables become more important, more blue or more red or grey, where there's like pretty neutral effect on the tree growth measured by the dendrometers. If you look at the Ashley train model applied on the data for the Ashley site, Temperature of the soil at 30 centimetres had a negative effect on growth, and air temperature, which is below that, had a slight positive growth over time, more or less consistent. At the Maharangi site, the soil temperature at 30 centimetres also had a negative effect, but was less important at the Maharangi site, and also air temperature was slightly less important for the Ashley site. Interestingly, looking at these two variables here for the Maharangi site, rainfall, precipitation and temperature had a very different effect at this season in autumn of 2023, and it was very different to what the responses were just before that period. That was picking up the effects of Cyclone Gabrielle at the site, because the Maharangi site is north of Auckland, and it was pretty much bullseye for the January 27th Auckland anniversary flooding event, and then Cyclone Gabrielle, and that had a net negative effect, or changes in the effect on the dendrometer growth after that period. So even though the model was trained in Ashley forest data, didn't see any storms like that at that data, the model was able to, the Ashley trained model was able to pick up the changes in environmental effects growth after Cyclone Gabrielle. And if you compare that to the Ashley forest, there was pretty much of a muchness during a similar period of time there. Thirdly, moving on to using neuroordinary differential equations to improve NASA SNAP satellite retrievals. NASA SNAP measures soil moisture, whizzes around the planet, measures soil moisture down to 5 centimetres depth, between 10 to 30 days a month, usually about 5 to 15 at best. And the results are measured using a passive and active satellite. So SNAP stands for soil moisture active passive radar. The active radar broke within the first 6 months when they set the satellite up in 2016. So they had the MacGyver solution, use the Sentinel data to go and get an active process in there. So it uses, the passive relies on 36 and downscale to 9 kilometre resolution. The data for NASA SNAP was validated for New Zealand forests with closed canopies, which beforehand we did forest flows that didn't think it would work because of the dense canopies in these type of forests, and also steep topography. Forest flows showed that was not true. Data fusion with low resolution but high frequency 9 kilometre NASA SNAP VWC, which stands for volumetric work content, with high resolution but lower frequency 1 kilometre NASA SNAP Central VWC. We wanted to see if we can get that resolution from about 5 to 30 days, so 1 to 3 days a month. Frequency of, say, with the downscale 1 kilometre NASA SNAP, which was, if you're lucky to get it every 5 to 30 days, one period, in New Zealand once that period of time. We want to try and get it to 1 to 3 day periods, and why we want to do that is that we can actually look at individual response to individual rainfall events. So we use a deep learning AI method that uses physics-based equations for, again, transparency, interpretability, and trust. So they give us a resolution, a 1 kilometre resolution, and high frequency detects rainfall events instead of waiting 1 to 2 weeks to get measurements from the downscale NASA SNAP Sentinel model. So this is looking at some of the results from the study over our 7 research sites. This is a paper that's just been submitted from different forest sites across the country. The blue line represents our measurements of soil moisture on the ground, our real data. The green triangles represents the NASA SNAP data, and you can see, like for Central Kaingaroa, there's a huge amount of scatter around those ground truthing. So it gets some measurements, picks up the frequency, so the flux of soil moisture from wet and dry periods, but it's really, really scattered. But when we use the node data for our soil moisture, that's a heck of a lot closer to actual ground truth data. So not only do we get a lot more frequency of measurements with this AI deep learning approach, but also we get a lot more accurate measurements of soil moisture at our different locations. So switching gears a bit, because that was a nice little geeky AI science, is talking about how we can turn this science to making a difference. So during the Forest Flows program, the Otago Regional Council proposed a land use rule that said that all radiata pine had to be removed within 50 metres of every stream channel in forest Otago regions. The reason for that was to somehow increases stream flow. However, there was no scientific evidence for that. They did not realise that if you try to remove trees from every single, not only had to, they want a riparian zone, a setback as we call it in the trade, and they want to remove all the trees in there, and they didn't realise the cost of the reduction in harvest, which is be approximately 40% of the area on the target forest regions being affected, but also the huge ETS liability that was estimated would have cost the target forest companies alone $980 million. So there was forest companies not very excited about that. And other councils were considering similar rules. So the Target Regional Council and the forest industry had opposing views, which they politely had a communication breakdown in 2024. And then the Target Forestry Group used forest flows data and analysis and results as evidence to kind of push back to get the proposed rules. And the central government intervened in October 2024 to kind of say, no, you can't have these rules in place. So 1 week after the central government stepped down, we had a workshop run by the Forest Growers Research, SCION, and invited representatives from the target forestry sector and the council to let's talk. And that was a bit of a challenge because we weren't sure what kind of conversations we were going to have there. But we had a meeting and we talked about both their concerns about both sides, and using forest flows data as like a benchmark of saying this is the truth or this is what was going on to help make the decision making, to help rebuild trust that workshop, and recognition that science-based approach was required. So forest flows and both sides recognised forest flows had a data that was too complex, so required tools and to convert results to more alternative format for decision making. And that kicked off the development of a primary sector growth fund proposal with MBIE for Forest Hydrology Toolbook Kit. And that proposal was developing a whole bunch of tools to interpret forest flows data set that is produced from the AI and more traditional statistical approaches, supported by industry, councils and MPI. And it's a collaborative workshop approach to identify key questions of what tools development. So everyone in the room, what information you need, what do you want to develop, and tools to develop clear and effective information and provide non-biased information as have an input. And that's key to build trust and develop mutually agreeable regulations. And this was not, would it be a heck of a lot harder if we didn't have forest flows in the first place, producing all this information that showed us information about tree water use, catchment water storage and release. And skip that. So that was quite an unexpected achievement of an application of the science for forest flows using the AI and non-AI methodologies. Finally, we want to talk about speeding up the science cycle. So we showed this diagram before, and it was, I said before, it was very much a big challenge to get the data to this point and we get to store the data. We can actually do the analysis. But there was one slight problem with this methodology. It's still very locked in the science kind of science-based approach of us getting the data, doing the analysis here, and getting the data at WIMS from Kafka, analysing data, and then presenting it to our stakeholders and end users. So how do we improve this part of the cycle? So, so we've been working with collaborators from a small company called Wi-Fi, and some other folks as well, to kind of take the Kafka approach and how do we kind of and speed up the science cycle from years to months by building dashboards for the Kafka data to be visible for stakeholders and landowners. And I really don't like this term, it's democratization of data, but it is very apt in this place, making the data available for your end users, for your local communities, for the iwi you're working with. It kind of informs them what's going on, and it helps them feel more connected to what's going on with these measurements going on their land and their communities. And we've been developing this prototype dashboard system to have a flexible way to provide analytics. So not just getting the raw data from Kafka, producing it into the dashboard and say, hey, here's some of our raw data. That's kind of cool, but it doesn't tell you much. So we've been working with Wi-Fi to kind of have a flexible system to do some analytics with the data, but not being rigid to say this is the only thing you can do. Work with your communities. What else do you want to learn? Oh, no, that's interesting results. What else can we dive into that data? And also been working with the University of Waikato, with Kahume there. We're developing AI prediction tools. We're interested in developing predictions of our dendrometer trees in advance. Why? Because like trees under stress gives an indication that the trees are under stress because of drought or disease, or like soil saturated with soil saturated, for example, gives a warning that this particular catchment may be prone to flooding if there's a large rainfall event coming soon, if there's another large rainfall event in the horizon that could also cause erosion. With the Kahume's work about looking at predictions from our data, we've done predictions about 10 days ahead of dendrometer growth, and we're working to improve it to about 30 days or even further ahead of prediction of growth. And also, all this information provides time information for decision making instead of like having a research program where hey, we're going to do this for 5 years and then tell you what the results are. We can speed that process up and say, this is what's going on. We're all doing some deep analysis with the data, and this is what's going on, which help people to understand what's going on in the results. So forest flows, in summary, forest flows have developed a range of technology, data management, AI analytics to achieve program goals, which is quite applicable to other complex environmental data, not just forests. Early and active engagement of landowners and stakeholders are important. Transparency, interpretability, and trust is important. It's been discussed a lot. Sounds good in theory, but it actually is quite important to bring your stakeholders, bring the communities along with you to understand what's going on. Also develop tools to speed up the science cycle instead of going from years to months and years to months. So finally, what's next is that we use the Forest Flows program and developed a new proposal through MBIE called the New Zealand NASA Joint Partnership Program, looking at Te Huku in the far north, looking at integration of data from terrestrial sensors and satellites to look at water use across the Aokori Peninsula. Where's the water going above and below ground in comparison to different land uses? But it's a very good opportunity to not only to further develop data fusion methodologies with AI, but also dashboard analytics to engage our communities. And that's also unlocked a partnership with the European Space Agency. So very, very briefly, this is a dashboard that's taken our data from the Kafka system. We brought thanks to Wi-Fi, brought the technology to kind of pull the data in through the Minnow system to bring this data into this web platform to have a look what that data is. So this is looking at information from our sensors, stem dendrometer data for 1 month in December 2021 and soil washer as well. And this is looking at just one site here, and this is looking at stem tree growth, and we've got these minimum and maximum thresholds of growth over one period. So if we change the threshold of, say, where's our unhappy trees, it picks up plot 3 and plot 9 behind the 8 border growth, and then if we move that up to there, so we can now go down to the map, and we can see across our research site there, the dark green circles is where the trees are growing, the plots where the trees are growing faster than average. And then we've got can't we see it? Plot 3 and plot 9 are the yellow ones, saying those trees are growing behind there. So that straight away, it's a visual way to say within this particular catchment, where are the trees not growing fast, not growing slower or growing faster. And if you can scroll down here, if we say this line represents the average growth of the trees across the entire catchment. If we just pick plot 10, we can put in here four dendrometers from this particular plot. And you can see 3 out of the 4 dendrometer trees are growing faster than the average, and one of the trees is growing below the average. So that gives straight away a visualization of that data, what's going on. What we want to do is kind of like make this screen kind of pop up when you click, make the map clickable and kind of look at the data over time. And then you can look at the soil moisture data as well, look at the responses through there. And again, if you just put some thresholding in place and say, what is say minimum 0.2, and say make that 0.3. And then we can see again different soil moisture responses over time, looking at where things are wetter and drier. And if you can remember what it looks like the dendrodrome data, just because some plots are drier, that product's drier, but the trees are growing faster in the location. Plot 9 had some slow growing trees, but the soil moisture is pretty middle of the road. So that straight away gives people information what's going on in their forests, where these research sites are going, and working with our good friends at the University of Waikato team is that we can build the analytics of the data, the climatic data coming through from meteorological stations, as well as say predictions into the future of how fast, predictions of how fast or how slow those trees are going. So, and it gives a chance to kind of interact with the local communities. What else information you want to know through here? But thank you.